Yes, hello everybody. We have two presentations today, and these two presentations are very special. They are not regular seminars. They are actually from the participants in the program Building Future Faculty. And I would like to say that this program is very unique. And if someone wants to be involved, then of course next year will be opening. And it's a very good program. It's about 2.5 days. We have two presenters. We have Dr. Zeinab Alsmadi, and we have also, Amanda from University of Illinois. And we will start with just 30 minutes for Dr. Alsmadi. She graduated from NC State here in 2020 with a PhD in nuclear engineering and a master's degree in material science. And so, her presentation is ready, and please come forward.
Thank you so much.
The stand is yours.
Thank you. Hello, everybody. I'm Zeinab Alsmadi. I am a postdoctoral research scholar here in the department. I work with Professor Burnham. I'm very happy to present in person since the pandemic has started. And I'm very also excited to be participating in the Building Future Faculty program this year. It has been a wonderful experience so far. Tomorrow's left, so I can't wait for what tomorrow we have. So today I'm gonna, as part of our participation in the program, is to present about our research, or briefly about what we do. Basically my research is based on nuclear materials, radiation shielding, and nuclear waste management. So my topic for today is about investigating the mechanical and shielding properties of an advanced austenitic stainless steel known as alloy 709, used as an application for future nuclear energy systems. So the first part of my research is about understanding the relationship between mechanical deformation of structural materials, their processing, their functionality, and their microstructural evolution. One of the reactors that are next generation reactors in specific are designed to have prolonged lifetime. They are designed to be safer, more reliable. One of the next generation nuclear reactors is sodium cooled fast reactor. Sodium cooled fast reactor will be the only midterm available fast reactor with acceleration in research and development, and also economic competitiveness. It uses sodium as coolant and moderator, and it operates at temperatures as high as 500 degrees Celsius. So the structural materials in sodium cooled fast reactor are subjected to, during startups and shutdowns, they are subjected to cyclic loading, which is known as, or result in fatigue damage, tension, and compression. And also the steady state operation and sodium cooled fast reactor introduce time-dependent effects like creep damage, which occurs at constant stress and temperature. So the effect of creep and the effect of damage, of fatigue together can be combined and the structural material, which cause a fast failure of the structural material of the reactor. This phenomenon is known as creep damage interaction. So one of the candidate structural materials that have been suggested to use as structural material for sodium cooled fast reactor due to its interesting mechanical properties is the alloy 709 advanced austenitic stainless steel. Includes 25% nickel, 20% chromium. It's strengthened by niobium and stabilized by nitrogen. Alloy 709 exhibits interesting mechanical properties like good creep properties, corrosion resistance, high thermal stability, and also high thermal stability and high temperature strength. So what I have done is performing creep fatigue tests on alloy 709 experimentally in the lab here in the third floor. It's nuclear materials group lab under the supervision of Professor Kale Morty. So how we perform the experiment, we have the electrodynamic creep fatigue testing machine from test resources, which we use a parallel gauge tested specimen of alloy 709. And we use extensometer to measure the strain change. Also, we apply high temperature to the experiment using resistive heating furnace from ATS. And all connected to software where we get the data, we analyze the data. So there are two types of creep fatigue tests. There's stress mode test and strain mode test. So the difference between these two modes is strain mode test is where we control the fatigue damage, or we control what strain the fatigue damage will occur at, and then the stress will varies, or the creep damage will change. The stress mode is the opposite, where we control what creep or how much creep damage or what the stress, at what stress creep damage will occur, and then fatigue damage or the strain will varies. So we have performed strain control tests of creep fatigue, and we studied different effects. We studied the effect of strain, where we performed at strains ranging between 0.3 to 0.6 strain amplitudes. We performed it at different temperatures, like 650 degrees Celsius and 750 degrees Celsius. We performed it at also different hold times. So what I mean by hold time refers to creep damage, because as we can see here in the stress strain hysteresis loop, here is the fatigue part, but the creep part here is referred by this area. This is the hold time region in which the stress relaxes. So here we specify what hold time we want. We set it from 0 to 1 hour. And what happened is the stress relaxes. During stress mode, what happened is the stress will stay constant, but the strain will vary. So the results from what we studied, the effect of temperature, strain, the effect of hold time, we observed that the number of cycles to failure, or the creep fatigue life of alloy 709, or the life in general of the sample itself, it decreases when we increase the temperature. It decreases when we increase the strain or the fatigue. It decreases when we increase hold time or the creep damage. So this all affects the material life itself. And so what happens is the material fracture. So also when we look at the hysteresis loop, we observe that when we increase the creep damage or the hold time, the width of the cycle increased because of increasing the inelastic strain that's developing in the sample itself. Thus, resulting from transformation of the elastic strain during stress relaxation. So another thing that was interesting to look at is time to failure. When we look at time to failure versus hold time at different temperatures, for example, 650, 750, we can see that at higher temperatures, time to failure is less than at lower temperatures. The material fractures faster. Also, we can see that with increasing hold time, time to failure increase. Somebody might ask why the time to failure increase with hold time, but number of cycles decrease with hold time. How come it takes more time to fracture, but its life is reduced? So there's no contradictory between the two observations. However, when we introduce additional time to the cycle, which is the hold time, the cycle time in general increased by a factor that is greater than the factor that corresponds to the reduction in the number of cycles or the creep fatigue life of the material. That's why we observe increase in the time to failure, but with hold time, while decrease in the number of cycles to failure with hold time. So this is what happens with hold time, the stress relaxation plotted versus normalized time. At different hold times, we have here 60 seconds, 600 seconds, up to an hour. It all follow the same trend in which once the hold time starts or the creep damage starts, the maximum stress drops and then it follows a steady state behavior. And so it follows a steady state behavior for a longer period because of longer hold time, and that's why the material is subjected to stress for a longer time, and that's why it fractures. One of the important things to look at whenever somebody is investigating creep-fatigue interaction is creep-fatigue interaction diagram. So creep-fatigue interaction diagram is important for design rules, safety criteria, because the purpose of this diagram is to develop something called envelope. Each material has an envelope in which separates between non-cracking and cracking. So it takes many, many years to develop such an envelope, a lot of data points, but we have the preliminary data points for HALEU 709. There are envelopes that are developed for 316s, 316 super alloys like 617. But here, so the creep versus fatigue damage, we have the preliminary data points at different temperatures, strain ranges, different hold times. And the way we get these data points is following the linear damage summation rule from ASME, in which it states that the fatigue damage here plus the creep damage here should be less or equal the ideal failure, which is equal 1. And the ideal failure here is the dashed line, in which data points here will be up, most of it below this line, and some of it will be above this line. So the envelope for HALEU 709, of course, it will take a lot of time to construct such an envelope. It will take many data points, like I said. But the higher fatigue damage means that the crack propagation is enhanced by cavitation damage, because what happens is on the microstructural level is that when fatigue happens, transgranular cracking develop, and fatigue damage results in intergranular cavitation, in which they interlink and become intergranular cracks. So transgranular cracks with intergranular cracks interact with each other, and the material fails. So, so while higher values of creep damage means that cavitation damage is enhanced by cyclic loading. One of the things also we look at whenever we study mechanical properties of structural materials is we look at the microstructure under the microscopes. We use optical microscopy to look at the free surfaces of the sample, and we notice that when we increase the hold time or the creep damage, we see that oxidation is penetrating through these cracks. Since oxidation is a time-dependent process, that means when we increase hold time, we will see more oxidation penetrating these cracks. So we observe wider cracks with longer hold times. Also, we look under the scanning electron microscopy on the fracture surfaces of the sample after it fractures. And we observe that here we can see, probably it's not very clear here, but we can see here the intergranular pre-cavitation red circles, and the white arrows refers to transgranular fatigue cracking. And when we increase the hold time more and more, the damage mode is dominated by creep. So we observe more intergranular cracks than transgranular cracks. Also, we look under the transmission electron microscopy, look at the dissipations, precipitates, etc. Under creep fatigue damage, we observe subgrains. Also, we observe chromium-rich precipitates. Also, we observe well-organized boundaries with network dislocation, which is unlike what we observe under pure fatigue tests, which is disorganized boundaries with tangled dislocations. Of course, all of these observations, they affect the mechanical properties of the material. The material will have eventually shorter elongation. It will have higher UTS, or the ultimate tensile strength, and it will have a reduced life. So it will fail faster. So this is the first part of my research. For the second part of my research is investigating the shielding properties of 709 as well. The story behind this part of my research, when fuel assemblies reach their capacity limits and reactor, they are transformed into cool to cool down, then they are stored in storage systems. But they still can emit high levels of radiation that can pose risk to the environment and the personnel. So it's important to make sure that the storage systems are shielded very well to prevent any radiation leakage. So this is a schematic of what a storage system looks like, and especially dry casts, spent nuclear fuel dry casts, in which the spent fuel is surrounded by stainless steel canister, and then it can be coated then by glass-based coating to enhance the shielding efficiency, and then the outer layer is the heavy concrete overpack. So I have been investigating with Professor Baram the shielding properties experimentally and computationally of the structure material of spent nuclear fuel dry casts. I studied the alloy 709 as a canister material compared to other stainless steel. And also I studied different coatings like the newly developed simulated amorphous materials and multi-glass-based coatings as used as a coating for the canister. So for the canister material, I studied alloy 709 compared to 304 copper, 303 copper, 304, and 316 stainless steel. They have similarities in the composition, but there are also some differences which can be related to their different behavior. So I performed this study computationally using Microshield. Microshield is a shielding assessment program. It's used to design shields, estimate their exposure rates, get their attenuation properties. It's based on the geometry that you're using, the dimensions, the material, the source that you are considering in the case. And the really nice thing about this software is that you can use it on any kind of material. You have the option to customize the material that you want to study its shielding properties. It's approved by NRC. It's based on deterministic code. It produced similar results to MCMP. This is very user-friendly and can give you results within seconds. It's just you have to know how to build your geometry. So this is how I build the design of the dry cast. I have the spent nuclear fuel in which it's surrounded by the canister material. In every case, I run different stainless steel canister materials so I can compare the results. And then I surrounded the canister with a glass-based coating. Glass-based coatings used because they have high density. They are used to enhance the shielding properties because they have high density, transparency to visible light, and they are also because of their thermal stability. And then the heavy concrete overpack. And this is the dose point here on the outer surface of the dry cast. After I run the case, I look at the linear attenuation coefficient and the mass attenuation coefficient. They are calculated using the equation here. The radiation intensity equals the initial or the radiation intensity E2 minus mu x. X is the thickness of the sample that I have, and the mass attenuation coefficient is the linear attenuation coefficient divided by the density of the material. So what we observed when I compare here between 709 and other stainless steel is that 709 exhibits a higher attenuation coefficient, which means it has a better shielding properties than the other common stainless steels that are used as canister material in spent fuel dry casks. Another properties we look at also exposure rate. Exposure rate here and compare it with buildup, of course, exposure rate with buildup, and compare it to the other materials. We can see here that the difference between the different stainless steel is significant at lower energies, but with increasing energy, the difference becomes not as significant as the lower energy. And also another important observation is that alloy 709 still offered a better reduction in exposure rate compared to other stainless steel. Also, we look at the half value layer. Half value layer is the thickness at which the radiation is reduced by half. So it equals ln2 over mu. And also the lower the half value layer, the better the shielding effectiveness. And still alloy 709 exhibited the lowest half value layer among other stainless steel. For studying the canister coating, we tried to study a new developed simulated amorphous materials. Simulated amorphous materials are newly developed iron-based metals. They exhibit high corrosion resistance. They are excellent nutrient absorbers, and they have also high hardness. So they can be applied to the cancer via thermal spraying. Their mechanical properties have been studied, but their shielding properties have not been studied. So we performed the same study using also a Microshield, in which we used the canister S709, and then we changed the SAMs. We have different SAMs that we studied with different composition, and we have also GlassBased. It's a glass-based coating that has a very high attenuation coefficient. So we wanted to compare with it and see how their behavior is like. And then we have the final concrete. We use concrete 6 with this composition. Also, concrete 6 is heavy concrete overpack that also exhibits a very high attenuation coefficients. So when we look at linear mass attenuation coefficient, we observe that the sand material that includes probably it's not showing here, the molybdenum and deuterium exhibits high attenuation at lower energy, but the SAM, which is to X5 that has higher density and includes silicon and manganese, exhibits better attenuation at higher energies. And also, when we compare it to glass 6 still exhibits better attenuation than SAMs. But what makes SAMs interesting is that they have better mechanical properties than glass 6 or glass-based coating, which makes them interesting to study as canister coating. Also, we look at mean free path. Mean free path is the average distance at which gamma ray travels before interacting with the material, and it's one over u. So the lowest the mean free path, the better the shielding efficiency. We also look at exposure buildup factor versus mean free path or penetration depth. Of course, exposure increase with increasing penetration depth, and we can see that difference becomes more significant between 3 materials at higher penetration depth. All these properties, shielding properties, can be obtained by Microshield software easily. Yeah, this is what we obtained. We actually published a paper recently on SAMs in nuclear engineering and design. Now, for the using another kind of coating on the canister material, we performed this experiment experimentally and computationally. We performed it in the lab on the 3rd floor. We used 316 samples. We don't have yet a 709 samples to deposit the glass-based coating on, but we have 316 samples, and we deposit on glass-based coatings, either single layer or double layers. The way we perform this on the experimentally, we have the scintillation detector here, sodium iodide detector. We place the sample between the detector and the sources. The sources we use barium-133, cesium-137, and copper-60. They have the following photon peak energies, and each one has a certain activity. So here, the results after we perform the experiment, that the number of counts decrease. This is the blue line, refers to no sample being or sample with no coating. And then the lines here below, or the reduced counts, refers to the sample where there is glass-based coating on it. Also here, the schematic here shows that the benefits of using glass-based coatings on the stainless steel. Titanium nitride here can be used as coating as a diffusion barrier. We can have blended zirconium, titanium, aluminum for corrosion resistance, and then we can have a 3rd layer of molybdenum sulfide as anti-crack. Also, we performed this study computationally using Microshield. We designed the same setup as the experimental one, also using the same sources, and we observed here. Here is the comparison between the experimental and the computational one. We observed there's fluctuation in the experimental results, unlike the computational ones where they decrease with increasing energy. The experimental values are higher than the computational ones. That can be related to the device sensitivity. The environmental effects also around can affect the readings that we are taking in the lab. But however, from all the different coatings that we use, like aluminum oxide, aluminum sulfide, titanium nitride, titanium oxide, zirconium oxide, we observed that the sample that has double coatings offers better attenuation than the one that has single coating or no coating at all. Which is also very good to enhance the shielding properties because you have very high density material, but a very small thickness, which helps in increasing the attenuation properties. For my current research at the moment, I am studying the corrosion properties of 709 because also in dry casts, self-accelerated corrosion was observed, in which corrosion was found at the interface between the canister, stainless steel canister, and between the nuclear waste. So it's important to also study the behavior of 709 under corrosion tests. So 2 tests are being performed. The first test is circulating salt brines, in which I immerse the 709 sample in corrosive solutions of different pHs for a prolonged time. And then I measure the weight change of the sample over the time. The second test is electrochemical polarization test. It's used to get corrosion rates versus temperature. We perform it at not high temperature, 20, 40, 60, 80 degrees Celsius temperature, because heat can come from decay inside the dry cast. So how this test go is to measure the flow of electrons that results from reduction and oxidation reactions due to corrosion. And we apply external voltage or current to disturb the equilibrium state, to cause non-equilibrium state, which is polarization. And that can allow us to get the corrosion rate in a shorter time scale. Also, this is connected to Gamry. This device is from Gamry Instruments. It's connected also to Gamry software, in which we get the data and we also analyze it to get the corrosion rate versus temperature. This is what I'm doing at the moment. For my next step in research, I'm interested in looking into a different field, fusion reactors. So fusion reactors, I'm interested in looking, also performing computational assessment of the protective coatings and inner critical components of fusion reactors, like diverter, first wall, vacuum. So this is it for me. Just want to show you research publications. I published also some papers with Professor Murray and other colleagues on pre-fatigue, and also published journal articles with Professor Brown and other colleagues on shielding properties. I also participated in ANS conferences, SEM conferences, and also TMS conferences, symposiums. So yeah, thank you so much. This is it for me.
Yeah, maybe a quick question, because we have another presentation. Any quick question to Dr. Alsmadi? Anything?
So I like the electrochemical corrosion accelerated testing you're doing. How do you extrapolate from, say, potentially applying to, say, a longer lifetime without a potential would happen in canister? So, like, how do you go from that to, expected lifetime for corrosion?
Well, we haven't done that so far. What we have done is we haven't extrapolated yet. What we're doing at the moment is just get the corrosion rate versus temperature. But the next step is to learn how to extrapolate the corrosion rate.
Any other question? Thank you, Dr.
Thank you so much.
Thank you. Amanda Bachmann is an AUP fellow, and she is from University of Illinois. She is finishing her PhD, so very soon we will call her Dr.
Thank you, Professor.
name is Amanda Bachmann. I'm a graduate research assistant in the Advanced Reactors and Fuel Cycles group at the University of Illinois. The Advanced Reactors and Fuel Cycles group was formerly run by Professor Katie Huff, who is now at the Department of Energy. It is now being run by Dr. Nadine Punk. So today I'll be presenting my work on the impacts of using HALEU, which is high assay low enriched uranium, on the nuclear fuel cycle. So first, providing a little bit of information about myself. I educationally have a bachelor's and a master's in nuclear engineering from the University of Tennessee. I'm working on my PhD in nuclear plasma and radiological engineering at the University of Illinois. Anticipated graduation date on that is August of 2023, but we're flexible on that one. Some of my previous research experience includes some multivariate modeling of radiation signatures for safeguards purposes. This is actually what I did for my master's thesis. Also modeling material flow through a pyroprocessing facility, once again for safeguards purposes. Comparing the effects of different Doppler broadening methods within SHIFT, which is a Monte Carlo code developed at Oak Ridge National Lab. And then finally, my current work investigating fuel cycle impacts of using high assay low enriched uranium on the nuclear fuel cycle. I tend to describe my research interests as really the intersection of the nuclear fuel cycle, non-proliferation safeguards, as well as scientific computing. So all of my research tends to kind of fit in some intersection between those three, with my current research kind of falling into that section right there. So introducing the project that I'm working on right now. So right now we have a lot of new advanced reactors that are being designed and looked at for possibly deploying within our nuclear fleet. It's a really exciting time. We see a lot of progress being made. There is one big difference though between these reactors and our current light water reactor fleet. Many advanced reactors will require HALEU. So this is uranium that is enriched between 5 and 20% in uranium-235. So it's still considered like low enriched uranium as far as safeguards purposes. However, it is more than the about 4.5% that we typically enrich uranium for a light water reactor fleet. We are using HALEU in these reactors because they'll allow for longer cycle times as well as higher burnup of our fuel. So you can get a lot more energy run for longer times to get a higher capacity factor with these reactors. To meet the expected HALEU demand, the Department of Energy has proposed 2 different methods to create HALEU. The first one is recovery and downblending of high enriched uranium stockpiles that the Department of Energy owns. Some of this is from EPR2 at INL, or possibly from Y12 or Savannah River site. There are a couple of issues that we have with this. One of them is these are pretty limited stockpiles. This isn't a great long-term solution in order to be fueling our fleet for the next 20, 50, even 100 years. It's a very finite amount of fuel we can have. Also, some of these stockpiles are known to have impurities of other uranium isotopes that we typically don't see within our fuel. For example, EPR2 fuel is known to have uranium-236 present in it, which is typically a neutron poison. So that can affect how your reactor performs compared to if you just have uranium-235 and uranium-238. The other way that we can produce HALEU is enriching natural uranium. This is what we currently do in order to fuel our light water reactor fleet. We take the 0.7% uranium-235 that we mine out of the earth, enrich it up to about 4.5% that we need. Right now, we don't have any facilities in the US that are licensed to do this. Current regulations actually have uranium enrichment at about 4.95%. So in order to do this, we would have to likely build new facilities, but definitely change our regulations on uranium enrichment. So in case it's been a little bit since you guys have seen the nuclear fuel cycle, I wanted to provide a quick overview of that. So this is considered a once-through fuel cycle. This is what we employ here in the United States. It's a once-through fuel cycle because fuel is burned once in the reactor and it is discharged into a disposal facility of some kind without undergoing any kind of chemical processes to separate out materials. So we see the big parts here of enrichment, which is what we are focusing on here with developing this new fuel cycle. And a lot of these steps will be dependent on the type of reactor that we are deploying. So if we add in a reprocessing step, this closes our nuclear fuel cycle. Fuel is sent to reprocessing, uranium, plutonium are taken out. We can recycle that back into our reactors as well. So this is one option that we have with some of these advanced reactors, especially fast reactors, because they can continuously burn some of these heavier actinides. I mentioned earlier that we can downblend and recover our HEU stockpiles. So if we were to do that, we would add that in as a step. right before fuel fabrication, but separate from any enrichment because it's already at that enrichment that we need. So what am I looking to do specifically with this project? Well, overall, I'm trying to explore how developing this supply chain of HALEU affects our nuclear fuel cycle here within the US. So the first thing I need to do is quantify the material requirements of transitioning to these advanced reactors. So we need to understand how much of this enriched HALEU do we need, how much natural uranium would we need in order to produce that enriched HALEU. And then, other things of concern include the amount of waste that's produced from these reactors. The next part is performance sensitivity analysis to understand how parameters of the fuel cycle transitions affect some of these metrics that I'm looking at. So the material requirements of our fuel cycle. So if I change things such as the transition start time or the amount of reactors that are deployed, how does that affect some of these metrics that I'm looking at? And that leads us into identifying potential fuel cycles that can be optimized based off of some of those metrics. So if we can understand from our sensitivity analysis that the transition start time has the biggest effect on the amount of natural uranium that we need to enrich to create our HALEU, then we can optimize on, well, if we want to minimize that natural uranium that's required, then this is a good time to start transitioning to these advanced reactors. Each of these bullet points here are really trying to look at how our reactors that we're deploying are affecting their fuel cycles. So for the last part of my work, I really want to flip that question on its head. I want to start looking at how does our fuel cycle impact our reactors? I mentioned earlier that our HALEU stockpiles have impurities in them that can affect our reactor performance. So I want to look at if we're using these HALEU stockpiles and downblending them to create HALEU, how does that affect our reactor performance? Do we still get the same cycle time that we are expecting for if we have pure fuel? Do we get the same burnouts out of our fuel? Things like that. So looking into some of the transition analysis that I'm looking at, so the real purpose of doing these transition analysis is because if we can understand that demand for HALEU from our reactors, then we can start to develop that supply chain and design facilities that can meet that capacity at the time that we need it. So some of the factors that we know can affect the demand for HALEU include the reactor type. So different reactors will have different masses of fuel within their cores. They'll have different cycle times and how often you have to refuel them. So that'll affect how often we need HALEU and how much we need it. Also the energy demand that we're requiring out of these reactors. Are we going to require that they produce 100 gigawatts of energy constantly for the next 50 years? Or do we need that production to grow with the general growth of demand? So those two factors combined really control a little bit of how much HALEU we're going to need within our fuel cycle. So we can model these transitions through something called fuel cycle simulators. These are computational tools that model our fuel cycle. They model the deployment and decommissioning of different facilities within our fuel cycle. So all fuel cycle facilities from mines to mills, to our reactors, to even repositories, but then they also model the transactions of materials between the facilities. So we can really see how much enriched uranium is being sent from fuel fabrication to our reactors each time. So they really give us that sense of what are we needing within our fuel cycle. So looking at the fuel cycle data modeling here, it does contain a lot of different assumptions. So we see that I am starting from the uranium mines, or initial source of uranium. It's going to be at that natural uranium percentage. And then it goes through the mill, conversion, enrichment, fabrication, and then we'll go down through our light water reactors into our repository. So those blue facilities really mimicking that simple once through fuel cycle that we have in our nuclear fleet right now. When I transition, we start to see in red here the advanced reactors. So those are deployed. And so now we have two different streams of fabricated fuel within our transitions, and we'll start to compare how much each of those reactors are going to need. So I'm modeling these transitions through Cyclist, which is an open source fuel cycle simulator. It models things on an agent level, which means that each facility can act as an agent. So we can model every single facility independently, as opposed to modeling things on a fleet level, like some other fuel cycle simulators do. So I'm modeling these reactors from 1965 to 2090. So using some historic data on when reactors are, specifically our light water reactors, have been deployed throughout the US nuclear industry. I am modeling the light water reactors, every single different different unit that we have in the United States is modeled as a separate agent within my simulation. So each unit can be deployed and decommissioned on its own schedule. I got that information on their commission dates from the IAEA CRIS database, so the Power Reactor Information Systems database, which also contains information such as their power rating. I assume that all the light water reactors that are not decommissioned by December of 2020 operate for 60 years. CRIS published their data as of December 2020 is what I pulled from, and it has information on reactors that are already decommissioned, but anything that's still operating doesn't have that information for. So that's where that assumption of 60 years comes into play. Finally, I'm modeling the transitions to begin in 2025, so kind of aggressive compared to what we're seeing with things such as the ARDP, the Advanced Reactor Demonstration Program, where those reactors are probably not going to be online until like 2027, 2028, and even then it's at demonstration scale. So this really gives us kind of a bounding case of like, if we really push and get all of this together and transition very soon, what does some of this look like? I also want to mention that for deploying our advanced reactors within these simulations, I'm having cyclists do that inside itself. I am not manually defining when these reactors need to be deployed. So within these simulations, I'm looking at two different advanced reactors, the USNC NMR, as well as the X-Energy XC100 reactor, both of them requiring HALEU. Some notes within their design criteria. The cycle length for the MMR matches the lifetime of the reactor. So these are really meant where you fuel them once, put into place, operate for 20 years, and then you just decommission. It doesn't undergo any kind of refueling. However, the X-Energy 100, XC100 utilizes online refueling, so we're expecting that would be a very constant, steady demand of HALEU in order to fuel those reactors. Another interesting note is the power output. They have some different outputs of 10 versus 75 megawatts electric compared to, you know, our light water reactors on gigawatt for most of them. So really, that's going to play into how many reactors we need to deploy based on which ones we are deploying. So I've developed 5 different transition scenarios to look at. Scenario 1 doesn't include any advanced reactors, it doesn't include specified growth. It really just models our light water reactors, so those facilities I showed in blue for the simulations. And it's really just to kind of get a sense of what have we needed from our light water reactors, as well as what will the industry need if we don't do anything and don't deploy any new reactors. The next 2 scenarios I'm looking at, 2 and 3, are both no growth scenarios. So it's saying that the advanced reactors need to supply the same amount of energy that our light water reactors are supplying in 2025 when we're starting that transition, and they'll just continue to require that amount of energy out of our advanced reactors. And then scenarios 4 and 5, deploying the MMR and the XC100 with the 1% growth in demand each year, starting from what the light water reactors are producing in 2025. So looking at some of the results now, so the first one that I wanted to look at is how well is the energy demand met in these transitions? And the answer is not that great, unfortunately. So we see for reference that the light water reactors are producing almost 92 gigawatts of electricity in 2025. So for those no growth transitions, that's the amount of energy that I'm requiring all the reactors to supply. In scenarios 2 and 3, we do see this gap here initially between about 2030 and 2050, where the energy demand isn't fully met. And we see that this becomes a result of how Cyclist is deploying those advanced reactors. Because again, I'm not directly counting or calculating when these reactors need to be deployed. I'm letting Cyclist do all that math for me. We also see a similar thing happening in scenarios 4 and 5, where initially between about 2026 and 2048, we're not quite meeting that energy demand. And by not meeting it, I'm really meaning like it's more than 5 gigawatts off. So it's pretty significant. We also notice a couple deviations in scenarios 2 and then in scenarios 4. It's a little hard to see. And we see it about every 20 years, which is the cycle time of the MMRs. So we are in one step having to decommission an MMR, and then the next step deploy a new one. So we have a little bit of a dip in the energy that's being produced. And that's just a result of that shorter lifetime of these reactors. We don't really see that in scenarios 3 or 5 with the XC100, just because they have that longer lifetime, and because of when they start being deployed and when I end the simulations, we just don't really see them being replaced. And as I mentioned, the initial gap that we see in all of the scenarios really is because of how Cyclist is deploying the advanced reactors, and it's really in a reactionary fashion to what's been done, as opposed to looking ahead saying, okay, well, I'm gonna have this shortage in the next month or so, so I need to deploy these many reactors now. So the next thing I looked at is the number of reactors that need to be deployed, and we see that, unsurprisingly, this really scales with the energy output of each of these designs. So of note, the last light water reactor is decommissioned in 2076. So this represents Wansford Unit 2, which went online in 2016. So you see in the no growth transition, so scenarios 2 and 3, advanced reactors are starting to be deployed in about October of 2031. And like I said, that energy gap between supply and demand really starts in 2030. So again, it's a reactionary fashion to what's being done. The 1% growth scenarios, we see the advanced reactors start being deployed in March of 2029. So that's about a 2.5-year gap between each of those energy demands on when these advanced reactors need to start being deployed. And even then, they could be deployed even earlier to prevent those gaps in energy supply and demand. Then just to give you some numbers, the maximum number of advanced reactors through each of the scenarios 2 through 5 respectively, we've got about 9,000, 1,200, over 17,500, then 2,300. So we see a large gap of when we deploy the MMRs and then the XC100s, just because of that difference in the power output between these reactors. And also to put that into some context, we have about 93 light water reactors currently deployed in the United States. So large gaps in the number of reactors that we need. So finally, the last metric I want to look at here is the mass of enriched uranium that is supplied to each of these reactors to keep them fueled. So we see in the top figure here, this is for fueling, this is the amount of enriched uranium that is sent to the light water reactors as well as our advanced reactors. So light water reactor plus our HALEU, and then the bottom figures is just the mass of HALEU that is being sent to our advanced reactors to provide just a comparison of scale between those two things. So the good sanity check for this is that until those advanced reactors are deployed, we see all the scenarios requiring the same amount of enriched uranium. So they're all requiring the same thing, which is good because before the 2025 transition start time, they all had the exact same facilities. We also notice in scenarios 2 and 4, so in the red and the purple there, we have some really large peaks and valleys in when we need to send enriched uranium to these MMRs. And that makes sense, right? Because the MMRs don't undergo any refueling, and we only have to fuel them when we need to deploy new ones. So it's kind of going to be in roughly like 20-year chunks. We also see with the XC100s in scenarios 3 and 5, we see a lot more consistency with time on the amount of fuel that has to be sent to them, because again, they're utilizing online refueling. So you're going to constantly be having to send some amount of fuel to them at all times. And it's also kind of interesting to note in scenarios 3 and 5, it's actually a smaller mass of enriched uranium that needs to be sent to these XC100s as compared to what's traditionally been sent to our light water reactors. So that's kind of an interesting thing to note there. So really, what are all of these results telling us? So first of all, the XC100s, transitioning to them can really better meet the energy demands that we're setting in these scenarios, just because they have that longer lifetime, and so we don't have to be deploying them as frequently compared to the MMRs. We also see in the MMRs, they have significantly more material requirements, so we need more enriched uranium to send to them compared to the XC100s, just because you have to fuel the entire core at once, but then we also have to deploy just so many more of them because of that lower output of them. We also see that the online refueling of the XC100 means that there's more consistency with time, less variability on what needs to be sent to these reactors to keep them fueled. We also see that changing to a 1% growth demand model of our energy means that reactors have to be deployed about 2.5 years earlier in order to meet that demand. Really, through all of this, if we can understand these material requirements of these transitions, that can help us develop that supply chain as well as design facilities in order to meet our fuel cycle needs. I will say this is just really a subset of results. I do have a paper published with more results and going a little more in depth on some of this work as well, if you want to check that out. So some of the ongoing work that I have associated with my dissertation here. So I'm still tweaking with the once-through transitions a little bit. One of the things I'm doing right now is adding in the actual license expiration dates for our light water reactors, remove that 60-year operation assumption, because right now most of our light water reactors are licensed to operate for 60 years, but some are only licensed to operate for 40, and some are even licensed to operate up to 80 years. So adding in that variability of our light water reactor lifetimes. I'm also going to start looking at quantifying the natural uranium that is required to create all of this enriched HALEU, as well as the amount of waste that's produced from each of these reactors, and add those metrics into some of my analysis. And then finally, I want to simulate some transitions to multiple types of advanced reactors. So what happens if we deploy the XC100 and the MMR in tandem? How does that look like? Or what if we throw something in like a small modular reactor, which doesn't actually require HALEU, but is likely to be deployed in tandem with some of these advanced reactors that do require HALEU. So how does that affect our supply chain and our fuel cycle? Next, I want to also model some fuel cycles with recycling included, look at how that affects some of our material requirements within these fuel cycles. So if we have the fuel from the advanced reactors, include the cooling time, because we will need to account for that, send it to a separations facility, and then create new fuel out of that and recycle it back through. How does that look on our fuel cycle? And then also, what does it look like if we use a limited versus a continuous recycle? So after we send material through separations, put it back into fuel, and then it goes into a reactor. If it can go straight into a repository after it's cooled, that would be a limited, so it's only going to go back through one more time, or a continuous where we also deploy a fast reactor and just continuously burn that fuel until it's just fission products that we can't do anything with. So how does that affect our fuel cycle as well? I also, again, want to look at some sensitivity analysis. So what happens if we change our transition start time to 2030 instead of 2025? You know, how does that affect our energy profiles? You know, likely light water reactors will be supplying a different amount of energy in 2030 as compared to 2025. So that'll kind of shift our energy demand, as well as just shift the rate at which light water reactors are being decommissioned and how many we have left. For the fleet share of the reactor, what if I'm deploying the XC100 and an MMR in tandem, but I constrain the MMR to only constitute up to 20% of our reactor fleet? How does that affect our metrics? You know, how many reactors do we need? How much enriched uranium do we need to support that fuel cycle? And then finally, for the light water reactor lifetimes, what if we say that half of them operate for 80 years, half of them operate for 60 years, and adjust the timing of our transition to some of these advanced reactors? And which of our metrics that we're looking at are most sensitive to each of these inputs within our models? And then using those results from our sensitivity analysis, really trying to come up with some optimized fuel cycles in order to do things such as minimize the amount of natural uranium that we need, minimize the amount of waste that's being produced, things like that. And then finally, like I said, all of this work right now is really looking at how our reactors affect our fuel cycle. So for the last part, looking at how our fuel cycle affects our reactors. So if we use our HAU stockpiles, downblend them to create our HALEU, and they have those impurities in them, how can that affect our reactors? Are we going to have the same flux out of them? Can we maintain the same K effective within our fuel? Can we still have the same cycle times? Also, does it affect some of our safety parameters, such as our reactivity coefficients? And this is really meant to be just kind of a bounding study. You know, you could write an entire dissertation on just this last question itself. And so just kind of get a sense of if we only fuel these reactors with this fuel with impurity, like what is like the worst case scenario, or even with these impurities, things will still be okay and it's not that big of a question. So I kind of just want to start to dive into this topic. So I would like to acknowledge that my work is being funded through an NEP fellowship through the, it is now they changed the office's name, it's no longer the Integrated University Program, but through the Department of Energy. Here are the resources that I have, and resource 2 is the paper that I published if you would like to read more information and read through more of my results. And then finally, just a quick summary slide, and I'll just take some questions if I'll have any.
That's good. Okay, see, any questions to Amanda? Any questions to Amanda?
Looks like we might have one in the chat. Have you considered the results from folding waste depleted uranium into the fuel cycle with breeders by any chance? That is not something I really looked into. I know that's something you can do. Some fast reactors, you might need to initially fuel them with some enriched uranium and then just use depleted uranium to keep them operating. That's not something I was going to consider within this work.
Any other question? Appealing? In the chat?
It's just the one
Just
from
one?
Professor Hayes right
Any
now.
question from Ian?
Did your model take into account the same amount of energy percentage that is currently being produced by nuclear reactors to continue to be produced by nuclear reactors?
So I'm looking only at the nuclear side of our energy, so I'm not considering that, nuclear is 20% of our total energy across the country and like comparing it with other sources of energy. That is something that you could include within the energy demand of the scenarios of, total energy is expected to grow at this rate and we want nuclear to stay at 20% or something like that. That's not something I'm considering right now, but it's definitely a parameter you can look at with this.
Any other question? Well, let us take another again and we thank you. Your presentation. We hope that you are enjoying this program. Thank you so much. Thank you. Wonderful.